Can you please see the slides?
Yes, doctor, we can see.
Okay, great. So today is our last session, and during first two sessions, we talked about some of the basic stuff, and like we talked about descriptive statistics, or I would say like univariate statistics, and some of the issues which we come across in quantitative data analysis related to data cleaning and data preparation. That was very important in a sense because that sets the basis for your main analysis. And if that foundation or basis are not set properly, or assumptions are not, or data has not been cleaned properly, your results are sometimes biased, and sometimes you end up leading to type 1 or type 2 error. So today we are going to multivariate stuff, which means like we will be dealing with more than one variables. So whenever you have more than one variable, we have like in sophisticated term, we call it a hypothesis. So whenever we are interested in determining the relationship between two or more than two variables, so that involves thinking about a hypothesis or writing a hypothesis and then testing it. Sometimes we don't have a hypothesis and we do this kind of stuff for exploratory analysis. For instance, we just have a data and we just want to see a trend in the data or just want to explore. And then sometimes, based on those insights, then we go back to the literature and try to explain it and try to create, a theory out of that observation, which we, came up from the data. So we are going to talk about four things. We are going to talk about correlations. This is pretty straightforward. It's not going to take a lot of time. And then we are going to talk about comparison of means. And in comparison of means, we are going to talk about like two components of comparison of means. Like we are going to talk about independent sample t-test and Innova. And towards the end of the session, we are going to talk about linear regression. There is one topic which was mentioned in the workshop outline, but I had to skip that. That was Minova. Minova is also like a third type of comparison of means, but because of the scarcity of time, I have to skip that. But I'll little bit explain it to you and you can learn it by yourself. That's not at all tricky if you, if you have the basics in place, like if you know the Innova, if you know that some independent sample t-test, you should be able to do Minova as well. Okay. Moving on, correlations, mostly we are concerned with bivariate correlations, Pearson correlations. And basically correlations look at the association between two scale variables. Here we are talking about scale variables. You can also look at the correlation between nominal and ordinal variables, but for the time being, we just stick to the scale variables. So the Pearson correlations are related to the association between two scale variables. Now, when I say association, it means that we have to see that if one variable is going up, what is happening to the other variable? Is the other variable is also going up, then we can say that there is an association between these two variables. Or if one variable is going up and the other is going down, that is also an association, but in a negative direction. So the possible values of the correlation coefficients that fall between 1 and -1, and it is represented by R. So whenever you see that R is equal to 0.28, 0.38, which means that we are talking about correlation. So it is always represented by a letter R, small r. Small r is equal to, for example, if we are saying that the correlation between weight and height is 0.28, so we would write R is equal to 0.28. So that means we are talking about correlation. So now I will go back to the SPSS to demonstrate to you that how we can do that. So I'm just unsharing the slides and I'll be sharing the data file. Okay, we will work on the same file, the sleep CED file. Now, for instance, now whenever you are interested in looking at the correlation, what you will be doing, you will go to analyze, and if you go further down, you will find here correlate. So again, I'm repeating, you will go to analyze. In analyze, you will come down, down here. You will see a correlate, and in correlate, you will click at bivariate. So you click the bivariate. Now again, another pop-up window will open. Now, the variables in which you are interested in looking at the association, you will just drag them to this variable box. So for instance, I'm interested in looking at the correlation between weight, height, general health, physical fitness, for instance, maybe alcoholic drinks. Oops, also I press the shift, so that's why it's problematic. So let me do it again with the control key. So you have weight, height, general health, like physical fitness, alcoholic drinks, maybe cigarettes per day. I'll just click on this arrow, and all these variables will be shifted from this box to this another box. You will see that by default SPSS will check Pearson and flag significant correlations. So again, and two-tailed. So again, these are the default options, and you will go with these. So whatever the correlations are significant, those will be flagged with star or 2 stars or things like that. If you click here at the options, you can also ask the SPSS to give you means and standard deviations of these variables, but maybe we are not interested in that. Okay, so, and one more thing. If you look here in the missing values, the default option SPSS is giving you exclude cases pairwise, which means that if we have, so when you have two variables on which SPSS is going to make a comparison or going to correlate them, if you have missing value on any one of those variables, SPSS would include the entire case. So this is what we mean by pairwise, only on those two variables. Okay, so you just let it like this, and you click OK. So I'm just going to unshare this, and I'm going to share the output file. Where's the output? Yeah, it's here, sorry. Okay. Okay, so now this is the output which you are getting. So it is a kind of matrix where you have the variables listed here at the top, and like here in the first column and in the first row. So this is basically a duplication. So now here you will see 1, 1, 1, 1, 1, 1. So anything above 1 and below 1, that's pretty much same. So for your easiness or easy to read, what you can do, you can delete the upper half. So I just double click this, and okay, so I press delete to make it more readable. Okay. So if now you look, can you see this table, please?
The correlation, the output, doctor? Yes.
This correlation where I have deleted the upper half.
We can see the output correlations. It's blurred.
This one is blurred.
Blurred means, doctor, this like lines kind of.
No, can you see this? The cells I am highlighting with black. Can you see those?
No, doctor.
No. So maybe it's opened at a new window, and new window is not shared. Okay, then let me go back to the old stuff. Okay, yeah. So now you can see, right?
Yes, doctor. The same
Yes.
table correlations. Yeah.
Same table, but no values in the upper half.
Yes. Yes.
Okay, great, great. Yeah, this is what I wanted to ask. So you see the upper half values I have deleted. So like similarly, you can edit the tables in the SPSS output as well, just by double clicking. And even like you can just copy paste these tables into a Word file, just right click, copy and paste it there. So if you look here, it is giving you N. Now this 249 means that there are 249 complete cases when SPSS was, because this is like weight with the weight. So weight with the weight is always 1. So that's why you will see a 1 here. So no need to interpret this. Now if you go to the second variable, you have height of the respondent with, now height of the respondent with the weight, sorry. Yeah, height of the respondent with the weight, the correlation is 0.56 and it is positive. And you can see it is significant at a level of 0.000. And there were 241 complete cases on which like we did not have a missing values while SPSS was creating a correlation for height and the weight. Now, the positive correlation 0.52 means that height and weight are positively correlated with a value of 0.562. That is a high correlation, quite high. Not quite high, but 0.56, because the maximum scale is like on a 0 to 1 or minus 0 to 1 and 0 to minus 1. So in that sense, it's a like high correlation, which means that if the height of the respondent goes up, the weight of the respondent would also go up. Okay, so which means that both of them are moving in the same direction. Or if the height of the respondent goes down, the weight would also go down. Now, if you look here at the general health, now the second, general health is negatively correlated and also significant 0.001 with the weight of the respondent. Now, this is, this is not in line with what the common sense says, because this means that general health would go down if the weight goes up. But usually we say that if the weight goes up, the general health uh, weight, yeah, general health will be done. Yeah, this is quite commonsensical that if the weight is going up, the general health is going down. So that's why the negative correlation you see here. Similarly, physical fitness and weight, you see a negative correlation at significant 0.01 level. Anything which is less than 0.05, for us, that is significant at 95% confidence interval. Cigarettes per day. Now, weight and cigarettes, the correlation between cigarettes per day and the weight is not significant. It's 0.20, but if you look at the significance value, it's 0.25, which is greater than a 0.05. So we say that there is no correlation between smoking and weight. And how many alcoholic drinks per day? So similarly, the correlation is 0.09, a significance level is 0.15. Again, this is not significant. So we can say that there is no correlation between alcoholic drinks one consumes and his or her weight. Similarly, you can interpret all other correlations. So you will take the second column and you will move down, correlation between height and general health, physical fitness, and so on and so forth. So this is what the correlation look like. Correlation is an important piece of information, and this is the first piece of information we look at in our data, because this tells us something about the data. And this also tells us that which variables are correlated with like positively or negatively which other variables. So it is always a good idea to run a correlation table or to make a correlation table of your focal variables or your variables of interests. So that always like that tells you some insights at how data is behaving. So that is the first thing which you are supposed to do, and that's pretty straightforward. So now I'm going to move on to the next, again, I'm sharing my slides. So now we are going to talk about the comparison of means. Now the comparison of means are, we have like two situations where we do comparison of means. And I'm sure that those of you who are working in maybe, in social sciences, and those of you who are working in biology, you come across these situations where you have to do comparison of means. Now, the first situation where we do comparison means is between groups. Now, for example, now what do you mean by groups? Groups means males and females. These are the two groups. Married and divorced. These are the two groups. Old versus young. These are the two groups. Now, for example, if I'm interested in looking at that, does the weight of weight in my sample is same across male and female, or are there any significant mean differences in weight across male and female? So this is where I'll be doing comparison of means. Or are there any significant differences among male and female on number of cigarettes they consume every day, for instance? So sometimes like we are interested in knowing these kind of insights, that how different groups in my data set, they behave uh, on on one of the variables of interest. Now this, we call it, this type of comparison mean, we call it independent design or between groups, because between groups we are comparing two groups. So two groups on a variable of interest. That might be cigarettes per day, that might be alcoholic drinks, that might be health rate, that might be weight, that might be height, and so on and so forth. Now, the second situation is within groups. Now, most of the time, people who are working in psychology, or who are working in these basic sciences like biology, they might have to do. For example, you have you have one group of respondents, and with whom you did some treatment, you administered some medicine, okay, and after administering the medicines, you just noted there may be blood pressure or any other indicator of interest which you are interested in. Now, after a few days, you will administer blood pressure of the same group without administering that medicine. Now you have the same sample, same group. So this is within group. So you have the same group, or we also call it repeated Meyer design. So you repeated some treatment with the same group at 2 times or 3 times, and then you compare that how their blood pressure vary. Now, for instance, if in psychology, I have a group of, okay, let me give you an example from my own field.
Doctor, can I ask you if we can make an example from this?
Yes, please.
From the College of Medicine. So we will make a randomized control trial. We will measure the blood pressure before and after the intervention.
Yes, exactly. Exactly.
So this is where it will be useful, right?
Yes, exactly. This is a pretty straightforward example. So doing any intervention, maybe you are asking them to go for exercise, you are asking them, to quit smoking, you are asking them to just administering some medicine. So that is an intervention. All these are interventions. So you are measuring the blood pressure before the intervention, and then you are measuring the blood pressure after the intervention. So you are just interested in knowing that whether the mean value of the blood pressure has gone down or up before the intervention or after the intervention. So we have to just statistically verify that whether are those mean differences are significant or not, because we cannot just say that, okay, before the intervention, the mean value of the blood pressure was, okay, maybe I'm talking about, this systolic blood pressure, or the mean value was 130. And when I did after the intervention, the mean value was 120. Now, by layman, we can see a drop. After the intervention, the mean value of the blood pressure has dropped from 130 to 120, but we cannot claim it that drop is significant. So for that, we need to verify it with the help of a t-test to see that whether that difference is significant or not, statistically significant or not. So we have so many situations where we use these t-tests, or we are interested in comparing the means. This is also used for experimental design. As I just mentioned, this was just the example you gave, that was just an experiment. Okay. And we use it when your independent variable is categorical with two categories and dependent variable is a scale variable. So in the second case, the example you gave, our independent variable was intervention versus non-intervention, and the dependent variable was blood pressure. In the first case, where I was giving you example between groups, our independent variable was gender with two categories, male and female, and independent variable was maybe weight or height. Now, the null hypothesis for this is that there are no mean differences between two groups. And the alternate hypothesis is there are mean differences between two groups, which means that you will accept the alternate hypothesis if p-value is less than 0.05. So you will look at the t-statistics, and if the significance level is less than 0.05, you will accept the alternate H1 hypothesis, which says that there are mean differences between two groups. Okay. Now, what are the assumptions of t-test? As I mentioned, in previous sessions, that we need to verify the assumptions for our data set. A normality for each group. Okay. So data should be normal, independence of scores. Now, this assumption you will see everywhere, which means that score on one respondent is not influencing the score on the other respondent, which means each case is independent. Okay. Independence of scores, this is for all statistical tests. And the third assumption is homogeneity of variance across groups, which means because we have two groups here in t-test, male versus female, or in within group design, the same group which was before treatment, after treatment, or before intervention, after intervention, the variance should be same or should be homogeneous. And when you run this t-test in SPSS use Levine's test to verify these assumptions. And H0 here says that the variance of the groups are equal, and H1 or HA says the variance of the groups are not equal. Now, in this case, we are interested that our variance should be equal, which means that we are interested in accepting the null hypothesis. And in this case, the null hypothesis would be accepted if p-value is, anyone? So we should look at the significance level or the p-value, and if the p-value is less than, someone on the chat, yes, exactly, p-value should be greater than 0.05. So if p-value is greater than 0.05, we would accept H0, which is null hypothesis, which means that the variance of the groups are equal. Now, don't worry, even if the variance of the groups are not equal, SPSS gives you two output. If variances are equal, you will look at that output, and if variances are not equal, you will look at that output. So SPSS basically adjusts the variance component in the final output. Okay. Now, this is how we report the results. This is what we are going to do it now. So I'm just going, I did it myself and reported the results here. If we are interested in knowing that whether the males and females differ on the mean weight in my sample, and if I see that this is they are different, so this is how I would write this. Males have greater weight. M is the mean value 82.45, and SC is the standard error 1.30. Then females with a mean value of 66.09, standard error this, and then I have to put the T in the bracket. You have to here just let me take this pen. This 247 is DF, which is like degrees of freedom. Forget about that, what is that, but in the bracket you just have to put DF. You will see this in the output, and this is the T statistics value and then the P value. So this is how we report the results. Now, for instance, now I am interested in you. I'm just doing an exploratory analysis, or I have this hypothesis that males have greater weight as compared to, or there are mean differences on weight between males and females. If I'm interested in you know in testing this hypothesis, how I would do that? Now I'm just unsharing the slides, and I'll go back to the data file. Okay, so this is the same data file, and I'm interested in knowing that do male and female differ on on the mean on the mean or average weight scores. So again, the same. I'll go to analyze. If you click on the analyze and you come down here, you will see compare means. Now, because this is my independent sample, so I would just click on this independent sample t-test. If you are running with the same sample, which means, you know, the example which you already gave, that if you are doing an intervention with the same group, you will use this paired sample t-test. But we are just, you know, doing independent sample t-test. So we would click this independent sample t-test. Now, wait, let me just remove this so that you understand from the beginning. Okay, so I'm interested my test variable or my dependent variable in this case is weight, which is a scale variable. And my independent variable is a categorical variable with two categories, which is sex. Now this sex has two categories. Now, when you put the sex here in the grouping variable, it tells you define groups, like which group you want to take as one and which group you want to take as two. Now, if you just look at your code book, you will see that we have coded it at 0 and 1. 0 was for the female and 1 was for the male. So I'll put here 0 and 1. I put continue, and if you here go to options, do not touch anything and press OK. So let me share the output with you. Okay, so if I here click on the output, this is your independent sample test. Now, weight of the response. Now, if you look at the here, this is the group statistics. If you look at the group statistics, we have 138 in the 0 group, and 0 group was female. And we have 111 in the 1 group, which was the case of males. So our group sizes are not equal. That's fine. And if you look, the mean weight of female are 66. And the mean weight of males are 82.5. So you can clearly see that the mean weight in your male group is higher. But we cannot claim it that this difference, because you can see that there is a difference of 16 kilo between the males and females on their average weight scores. But we are not sure that whether this difference is statistically significant or not. So we'll just move down to the other table, which says independent sample t-test. Now, as I mentioned earlier, that SPSS gives you, because we have one of the assumptions of homogeneity of variances, or variances across two groups should be equal. And I told you that SPSS gives you Levine's test for equality of variance result. Now, if you look at the Levine's test here, now this is this 1, 2, you know, this is the value for the Levine's test, because Levine test gives you the F statistics and the significance value. Now, the value of the F statistic here is not significant. So if it is not significant, what does it mean? To go back to the slides, I told you, remember? What was my null hypothesis? Now the null hypotheses are that the variances of the groups are equal. And my alternate hypothesis was the variances of the group are not equal. Now your p-value, you don't get a significant p-value because the p-value is not less than 0.05, p-value is 0.649, which means you would accept the null hypothesis. And the null hypothesis for this case says that the variances of the two groups are equal. So well done, Ali. Yes, it is that the variances of my groups are equal. Now you can always get an idea that the variances are equal or not. For example, if you look here at the standard deviation, what is the standard deviation for both the groups? From this table, can you get an insight that whether the variances are equal or not? Just a layman guess from this table. Anyone? Speak. You guys are sleeping, or you are, because it's Ramadan and you are hungry, you are thinking in your mind about iftar or what? Anyone? How come, Nigat, how come we can say that these are almost equal? We are talking about variance, but this is standard deviation. How can you say that these are equal? You know, look, standard deviation is also, because when you take the square root of the variance, you will get a standard deviation. So if you look here, the standard deviation of my zero group, which was the female, is 12.2, and standard deviation of my second group, which were male 1, is 13.7. So from here we can get, like, from a layman, you know, or just by eyeballing, we can see that these are almost equal. So which means that these are not significantly different from each other. So, and that's why, you know, that is being verified here down, that if you look at, you need to get a non-significant Levine's test statistic if the variance are equals. Now, if you look here, now this is the t-test here, values. Now you have two rows, equal variances assumed and equal variances not assumed. Because your Levine's test is non-significant, which means that now both the groups, males and females, they have homogeneous variances. So we will look at the first row, not the second row. Now, if you come here, now from this line onwards here, you have the t statistics, which is minus 0.9.9. And then you have the degrees of freedom. Now, degrees of freedom are determined by your data set. So just forget about that, that how it is calculated. But it's usually your n minus 2 in the case of groups, or n minus number of groups. So your sample is 8, 1 plus 9, 249. So 249, you have two groups, 249 minus 2, 247. But you don't need to do that. I'm just giving you an idea. And if you look that here, the t-test is significant. Here, the significant, it's 0.000, which is less than 0.05. And if you remember, our H naught in independent sample t-test or in comparison of means is always that there are no mean differences. That is our null hypothesis. And our alternate hypothesis are there are mean differences. And as the p-value is less than 0.05, which means we tend to accept the alternate hypothesis and tend to reject the null hypothesis. And this is the mean difference, same, minus 16.36. So minus 16.36 means you minus like 66.09 minus 82.49. Forget about the confidence interval. So now my hypothesis was that there are mean differences on weight between male and female. So is my hypothesis supported or not supported? Anyone? Anyone in the class who is not sleeping? Yes, good. My hypothesis is accepted because we get a significant p value here. Great. So it means you guys are not sleeping. That's good to know. Okay. So this is how you can see it's pretty straightforward, pretty simple, and pretty doable. And you come across situations where you have to run mean comparisons. Okay. Now, what if we have more than two categories? Because t-test is only used the two conditions. T-test is used if your independent variable is categorical, having two categories, and your dependent variable is a scale variable. So we have to look at our hypothesis. For example, our hypothesis says that there are mean differences between male and female on weight. Now, weight is my dependent variable, which is a scale variable, and my independent variable is male and female, which is a part of a variable, which is, here in data set is gender or sex. So independent is a categorical with two categories. Dependent is a scale. So the first thing which should click my head is, wow, I should be using a t-test because my independent variable is categorical with two categories, and dependent is scale, continuous variable. Now, what if we have more than two categories? Now, in that case, we will not be able to use t-test. Rather, we will be using Innova. Now, Innova stands for analysis of variance. So let me unshare this output, and I'll go back to my slides to, okay, what if both dependent and independent variables are categorical? If the sum, in that case, we will be using chi-square. Unfortunately, we are not covering it here. But if your dependent and independent both are categorical, you will be using chi-square. Chi-square is another test. So we are not talking about here, but this is just for your own information. Okay. You will find here in cross tabs the chi-square in analyze. Okay, so moving on. So I'll just unshare this output and I'll go back to the slides. So we'll talk about the conceptual foundations of Innova, and then we'll come back to demonstration part. Okay. So if your independent variable have more than two categories, then you cannot use t-test, you have to use Innova. Now, in t-test, you get t-statistics, and you have to look at the associated significance level of the t-statistics. But in Innova produces f-statistics, and you have to look at, again, the significance level of the f-statistics. Now, Innova also has the same assumptions, just like the t-test: normality of data, homogeneity of variance, and independence of observations. But again, don't forget, like, don't worry if even if like you don't find the homogeneity of variance across your groups, SPSS again will give you an option that you can look for the output where the variance is homogeneous. Okay. Now, the first thing you have to look at, because you have more than two groups. So the first thing you have to look at is that whether your test result is significant or not. So if the test F is significant, then we will go to the next level, because now F test will only tell you that there are significant differences across groups, but will not tell you that this difference is present between which group and which group, because now you have X, Y, and Z. So the difference might exist between X and Y, the difference might exist between Y and Z, and the difference might exist between X and Z. So you have three possible differences which might exist. And if any of those differences exists, the F statistics would be significant. Now, the next question comes that how we can explore further. We can take a deep dive to see that which of my groups are different from each other, or which groups mean differences are significantly different. Now, in that case, we use two types of approaches. One is the contrast approach or planned comparisons. Now, this is a little bit tricky, so I'm not going to discuss it here because we don't have enough time. And the second one is pretty straightforward, which is post hoc comparisons. SPSS also gives you options to select different post hoc comparisons. So once you check that, it would give you results of mean comparisons between two specific groups. So typically when we have planned, like when we have specific hypotheses, we go with planned comparisons or contrasts. But when we are just exploring, we do not have any specific hypothesis. We are just digging out the data. In that case, we go with post hoc comparisons. So if you just search Google that how to do planned comparisons or contrasts in Innova, it will tell you, because in this case you have to sign weight. So that was a little bit tricky. So I thought that we will not get enough time to talk about this. So I'm just talking about post hoc comparisons here. Now the post hoc tests which SPSS gives you, these are used when you do not have any specific hypothesis and when we are interested in comparing two groups. And as I already mentioned, that these are used mostly in exploratory analysis. Now, SPSS gives you a lot of options to this a lot of options to for the post hoc tests. Now, which post hoc test you should be using, that depends on that does that test control type 1 error, does the test control type 2 error, and how reliable that test is when assumptions of Innova are violated. Assumptions of Innova like normality, assumptions of, or when the two group sizes are unequal or equal. So in the next slide, you will see the whole detail. For example, these are the tests, post hoc tests, which SPSS gives you. Now, Bonferroni's, this is one of the tests. Now, this test is very good in controlling type 1 error, and when number of groups are small, like not like you have 10 groups, 8 groups, like when you have 3 or 4, 5 groups, this test is more powerful, and you can use this test when variance among groups is homogeneous. Don't use this test when variance is not homogeneous. Similarly, Tukey's, that also controls type 1 error. Tukey's you should be using when there are large number of groups. And this should also be used when variance is homogeneous. REGWQ, again, this is very good in controlling type 1 error. And this is again a powerful test, but this should not be used when there are different group sizes, which means like in one group you have 10 people, in another group you have 20, like 50 people. So there's a different size variation, so you shouldn't be using that. And you can also use that when variance is homogeneous. Then you have Hochberg's GT2, when you have different sample sizes across groups, and also when variance is homogeneous. Gabriel's different sample size across groups, but should not be used when sample sizes are very different, very much variation, and variance is homogeneous. Donut C and Games Oval, these are the two tests which we look at when variance are non-homogeneous. Usually my personal preference for when I use this, my personal preference is usually with Bonferroni. Most of people use Bonferroni when when you have a homogeneous variance. And Donut C people typically use when variance is non-homogeneous. So Games Howell is equally good, but these are the conditions under which these tests work very well. Uh, Sometimes you might see that all the tests are giving you the same results, but under extreme situations when maybe number of groups are too large, sample size across in groups is too much different, you see that different tests are giving you different results. So maybe you can look at this description to select that which specific test you should be using. Okay, now I'll go back to the SPSS and to demonstrate you that how you can do that. And just stop sharing and I'll open the data file. Okay. Now, for instance, I'm interested in knowing that are there any significant differences across categories of marital status on current weight scores. So maybe this is my my hypothesis, or this is my exploratory analysis that I'm interested in doing. So I go to analyze. You go to analyze again. You will go to compare means, and in compare means you will go to one-way Innova. Here, I click on one-way Innova. Again, let me put it back. So this current weight I'll put here in the dependent list, because again I told you that dependent variable should be a continuous variable. And marital status I will put in the factor. Now factor here represents the independent variable. Now this is what I was telling you, the contrast part, but we are not doing contrast part here. If you click here, contrast part here, basically you have to give coefficient for each and every possible category. First you have to create your contrast diagram, decide on the coefficients. There are like different conditions which you have to meet, and then you will keep on adding here. And then you also have like whether it's a linear, quadratic, cubic, fourth, fifth, and so on and so forth. This is a bit tricky, so complicated, advanced level. So we're not talking about here. But if you are interested in knowing, if you have a specific hypothesis and you are interested in learning about that, you can learn it. You will find videos on YouTube, Google. You can do that. So okay, so this is current weight is my dependent variable, and my factor variable is the marital status. If you look at the marital status, how many categories we have on the marital status? If you look at the sleep data code book for sleep data, we have 4 categories where one is single, okay, 2 is married, 3 is divorced, and 4th is widowed. So this is what we have data set. So because we have more than 2 categories, so we cannot use t-test here, because my independent variable is a categoric variable with more than 2 categories. So I'll be using one-way Innova. So if you click here on the post hoc, so you will see you have LST, Bonferroni. Now you will see all those tests which we just talked about. Now, for instance, I'm just going to click those, all of those which we talk about. We talked about Bonferroni, so I clicked Bonferroni's. We talked about Tukey's, so I just clicked Tukey's. We talked about REGWQ, this one, so I'm just clicking that. What else we talked about? We talked about Hochberg GTU. We talked about Jabriel. So Hochberg GTU, Jabriel. These are the most commonly used. You have some of others like SIDAC, Genkan, Tukey's B, Junet. So forget about that. Just click LST. Okay, I'm checking. And equal variance is not assumed. So because at this point in time we don't know that whether variance is equal or not. So we can just select from equal variance not assumed. We talked about Dunets and Games Howell. So I'm just going to check Dunets. I'm going to check Games Howell. We are interested in knowing significance level of 0.05, not 0.01. So we just stay at its default option. So I press continuous. If you click here at the options, I'm interested in knowing like this homogeneity of variance tests. That's it. The rest, no need. Okay, so once I press this button, okay, let me share the output and then we can talk about that. Okay, stop sharing, share screen, output. Aha. So you will get a big output here. Okay. Okay. So first, as I told you that we need to look at the value of F statistics. Okay, you just look at the test of homogeneity of variance. Now homogeneity of variance, because we are interested based on mean. So Levine's statistic is 1.3 and the significance is 0.26, which means this is not significant. Now, when it's not significant, what does it mean? That the variances across groups are homogeneous or non-homogeneous?
Homogeneous.
Sorry?
Homogeneous.
Homogeneous. Very good. Well done. Good to know that you are, you guys are attentive and listening to me. That's great. Okay. So we see that this is not significant, which means that our assumption for the NOVA, which was that variance across groups should be homogeneous, that is fulfilled. Okay, if you go down, I told you that the first thing you would look at is the F statistics. Now here the F statistics tells us this is between groups. We are looking at the between groups. It is significant, 0.02. Now significant F statistics or significant ANOVA value here means that there are significant differences across groups. But in this case, how many groups I have? Anyone? Can you recall me? Anyone? How many groups we have here?
5 groups, correct?
We have four.
Sorry, four, yeah.
We have single, married, divorced, widowed.
Yes.
So this significant value tells us that there are significant differences across group. But in t-statistics, the t-test, it was pretty straightforward that when the value is significant, we say wow, because we had only 2 groups, and you can say that the mean value is different. But by just merely looking at this value, we cannot say that which groups are different from which groups. Now, for example, there are 4 groups, and there are like a number of combinations, because at one point in time we have to look at 2 groups. So for that, as I already mentioned, we have to use post hoc test. Now, for instance, what do you recommend me? Which test should I be using? We have the equivariance, right? Homogeneity of variance is equal. And if we look at the group sizes, we will see it. If you group, for example, now you down here. For example, let's look at the Bonferroni, because Bonferroni is a good one. Now, if you look here, now what we are trying to do here, we are comparing single group with married, divorced, and widowed, and then married group with single, divorced, and widowed, then divorced group with single, married, and widowed group with single, married, and divorced. So whatever possible combination is, we are doing it here. Okay. Now, when we compare, now this single is our I, and the second column is J. So, and the mean difference is I minus J. So basically what SPS is doing here, it is subtracting the mean of singles from the mean of married to come up with a value. Now, the first thing you have to look at is that whether that mean difference is significant or not. Now, what is the p-value here? P-value is 0.24, isn't it? Can you see that? Hello?
Yes, we can see
Yes,
it.
doctor.
Okay, great.
Yes.
So, so the mean like this value is, the significance value is 0.04, which means that the mean difference between single and married is significant. The mean difference on what? Mean difference on weight. Now, which group has a higher mean? Single, out of single and married. Which group has a higher mean? Anyone?
I think the married, because it's when you minus, when you
Yes.
subtract it, you got a negative number.
Yes, exactly. Very good. Because now what SPSS is doing here, SPSS is minus I minus J, which means the mean of single minus mean of married, and results into a negative, which means the mean difference is negative. So the J, they have a higher mean. That's why you end up in getting a minus mean difference. So married have higher weight as compared to single. Does this make sense? If you think common sensically, does this make sense that married have, yes, when people get married, they tend to grow in all directions. So so that's what we found here, that the married, they have a higher weight as compared to single. Now, if you go down, we see that when we compare single with divorce, the mean difference is not significant. When we compare with, single with widowed, we don't find this is not significant, because significant differences are marked with a star. Okay, so this is the first thing. When we compared single with other, we found that there is a difference between mean difference between weight between single and married. Now, coming back to the second comparison, now married single, you find the same difference. None of the other is significant. You can also look at here the star value, and you can also look here at p values. Similarly, when we compare divorced with single, married, widowed, we don't found any mean difference any difference, significant difference. And when we compared widowed with single, married, divorced, we don't find any significant difference. So the only significant difference we found is between single and married. So the married people, they tend to have higher weights as compared to single in our data set. Okay, clear? And now this is what we compared it based on Bonferroni. But you see that it's pretty much same. Like if you see that Tukey's HST, we found the same result. If you go down and you find, you look at the Jabriel's post-hoc, we found the same. Hochberg, we found the same. So it's pretty much same, whatever post-hoc test. As I already mentioned, that as long as your assumptions are too much deviated, like you have a very big, very large number of groups, you have a very huge differences in the number of respondents across groups, then probably sometimes you see minor differences. Otherwise, most of the time, you just have to keep in mind one thing, that if the homogeneity of various assumption is fulfilled, just go for the tests which are mentioned here. And if it is not fulfilled, then you can go for these donuts and Games Howell tests.
Professor, question.
Yes. Yes.
My name is Laia, and I was wondering if I was doing a non-parametric test, all right? For instance, a general linear mixed model, all right? And I have all the results and everything, and I decide to do post-hoc analysis. Can I use Bonferroni for the post-hoc, even if my data is not normal? Or shall I use a different one?
Yes, you can use Bonferroni.
Okay.
It's a very powerful test, and most of the time people go with that.
Okay, because the other
Find any
thing
differences? Yeah, sorry.
normal, and I was scared that I couldn't use it in this case.
You know, if your data is quasi-normal, you can use Bonferroni. Quasi-normal means if your skewness kurtosis is within a range of +-2, you can use that.
Okay, perfect. Thank you very much.
Okay. Okay, so this was like Innova. And one more thing, you know, which I mentioned that I didn't include it in today's session because we didn't have time, but I'm just going to give you an overview that was related to Minova. Now, Minova we use when you have more than one dependent variables, scale variables, and on the independent side, you have a categorical variable. For example, if you are interested in looking at, you know, this, you're interested in looking at the mean differences across weight, height, health rate. So you have more than one dependent variables of the marital status, you will use Minova. Now, how to do that? You will go to analyze, you will go to this general linear model, and then you will go to multivariate. So this is the box which will be open. This is used for Minova. Here you will put your dependent variables. If you have more than one, here you will put your independent variable, and here if you have any control variables. And then, you know, you have the same postdocs and things like that here as well. That's the only difference. Okay, so I'm going back to my slides. One last thing we need to cover before we leave, and that is the linear regression. Now, the linear regression is used when both of your independent and dependent variables are scale variables, continuous variables. Linear regression or other types of regressions like logistic regressions. Now you will use logistic regression when your independent variable is categorical and you are interested in causality, not the mean differences. Independent variable is a scale. So what is the difference between causality and correlation? Now correlation or association only tells us that one variable vary when there's a change in other variable. Like if one variable goes up, the other variable also goes up. If one variable goes up, the other variable may go down. But it's not telling us that which variable is predicting which one. So whenever you have hypothesis where you are talking about cause and effect, there's this variable X is causing Y, that is causality. And for causality, we use regression, linear regression. Now, there are some of the assumptions of linear regression. Your data should be normal, pretty much we see it everywhere, or quasi-normal. Linearity, the type of two variables you are looking at, those should have a linear relationship, not a quadratic relationship, not exponential relationship, a linear relationship, which means the rate of change is linear. And the third is multicollinearity. Now, multicollinearity is that your independent variables, if you have more than one independent variables, those should not be strongly correlated with each other. If they are strongly correlated with each other, now that is, which means your results are going to be biased, or you have to remove one of those from your regression equation or from your model. And the last one, independence of observations. You also get the multicollinearity output when you run regression. You get statistics with the help of which you can see whether there's a multicollinearity in your data or not. Okay. Now, for instance, this is just an example. We are interested, or this is our theoretical model which we are testing. We are saying that physical fitness, there are 4 factors which predict physical fitness. Now again, I'm talking about prediction. I'm talking about causality. The first one is the energy level. The second one is the age. Third one is the number of alcoholic drinks you use every day, and the number of hours you sleep every day. So my hypotheses are that age negatively predicts physical fitness, which means the higher the age is, the lower will be the physical fitness. Energy level positively predicts physical fitness. There's a positive relationship between energy level and physical fitness. Alcoholic drinks, the more alcoholic drinks you consume, your physical fitness will be lowered, negatively predicts, and sleep hours positively predicts. More you sleep, probably more you would be fit. I'm just, because we make hypotheses based on theory, but these are just based on my common understanding for demonstration purposes. So when we run the regression, we are interested in, you will get like, these are the statistics you should look at. Now, you should look at the tolerance value and the VIF. VIF is variance inflation factor. VIF stands for variance inflation factor. So typically tolerance, if tolerance is less than 0.1 and variance is VIF is greater than 10, now this indicates a presence of multicollinearity among your independent variables. Now let me go back to the previous slide. Now by multicollinearity, it means that there should not be very high correlation between energy level and age, alcoholic drinks, and sleep hours. So all of these four variables should not be strongly correlated with each other. This is what you mean by multicollinearity. Okay. So the first thing after looking at this multicollinearity statistics, we also look at the F statistics. F statistics should be significant. If the F statistic is not significant, which means that our model overall is not significant, which means that the predictors which I have put in, either those are not supported by the data, or either there is a flaw in my theoretical thinking. I have not put the right predictors. And one of the most important statistic in regression we look at is the R square. Now R square basically tells us the amount of variance, the proportion or the percentage of variance explained independent variables by your independent variables. Now the maximum possible is 100%, but that is never achieved in any of the regression results. So if you do not have the strong predictors, or if you have the predictors which are not related to the dependent variables, you will get a low R square value. So whatever variance, you remember in the first session we talked, the more variance you have in your data, that is always good. So the variation in your dependent variable, how much that variation is being captured by set of these four variables. There might be other factors which are predicting physical fitness. That's why you never get 100% R square. So the more relevant factors you put into your model, into your regression equation, the higher the R square values would be. And then after looking at R square, you will look at the beta coefficient. Here we use the term B, not B, like beta, beta like this. Beta. R we used, as I mentioned, for the correlation, and the beta is for the regression. So then we look at the beta coefficient. Beta coefficient basically tells us the strength of the relationship, how strong there is the relationship between one of your independent variable and your dependent variables. And by looking at the associated p-values, like that tells us that whether our hypothesis is supported or not supported. If the p-value is significant, your hypothesis is supported. If p-value is not significant, your hypothesis is not supported. So I'm just going to unshare this and going to go back to the data file to demonstrate you that how we do regression in SPSS. Okay, so this is the file, the sleep file. Now my model, if you look at the slides, my model was that I'm interested in, let me go back to the slide to see what my model was. Okay, So my model was that I'm predicting physical fitness with the 4 predictors or independent variables: energy level, age, alcoholic drinks, and sleep hours. So what I'll do, the same tab, analyze, I'll go to analyze. If you come down, 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 you will see a regression. Okay, again, analyze, regression, and linear. So I'll under linear. So just let me remove this. These are okay. So my model was physical fitness is my dependent variable. So where is the physical fitness? Yeah, here is the physical fitness. So physical fitness is my dependent variable. Now, one more thing. If, for instance, these are the labels, and if I'm interested in, I want SPSS to display here, not the labels, the variable's name, I just can click here and click this box, display variable names. So you see now you have the trim or the variable names which are using in your data set. Again, I can click here and I say no, display labels. Okay, so this is a physical fitness and I had 4 predictors. It was how many alcoholic drinks you consume, sleep hours, weeknights during weekdays, every day, not weekends, and also age and alcoholic drink. How many? No, alcoholic drink. I'll support there was one more. Energy level. Yeah, sorry. So energy level was somewhere here. What is your energy level? I put it here. Okay. Now you go to the statistics. Okay, you check estimates, model fit, R-square change, descriptives, collinearity diagnostic. So you just keep it like this. And I click on OK. So let me share the output file. Okay, so these are my regression results. So this is because we asked SPSS to give us the descriptive. So these are the descriptive: physical fitness, mean, standard deviation, how many alcoholic drinks, mean, standard deviation, weeknights sleep 6.7 hours, age, average age is 43.95, average energy level is 6.46, and we also have the associated standard deviation. You can see that how much data if you don't replace and if you don't the missing values properly, how much data loss we end up in having, because our sample size was 271, but you see that SPSS is only using 106 here by using list-wise deletion, which means that if there is a single missing case on one of these variables, SPSS excludes that. That's why sometimes it's always a good idea to deal with the missing values properly before coming to the main analysis. Okay, now, so these are the correlations. We already looked at it, just forget about that. If you go down, 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 down here, aha. Now, as I told you that the first thing we need to look at your F, you can see that the F statistic is significant, which means that overall my regression equation or model is significant. So I can go ahead with the interpretation of individual betas. And similarly, if you look at the R-square value, now R-square value here is 0.173, which means the R-square value is 17.3%. Now, R-square is one of the important statistics, which means that physical fitness variation in my physical fitness scores, 17.3% of that variation is being captured by these 4 factors like energy, age, alcoholic drinks, and hours of sleep. And it makes sense because there are countless other factors which predict the physical fitness. These 4 are not the only factors which predict your physical fitness. That's why you end up in having like 17.3% R-square value. But as long as it is significant, we are good to go, which means that this proportion of variance, which is being explained by these 4 predictors in physical fitness, that is significant, and we can go ahead. The next thing which I told you earlier is we will go to the coefficient side. Okay, before going to the coefficient, we'll look at the tolerance. Here you can see the tolerance value and VIF. Now the cutoff value, I told you that the tolerance value here should not be less than 0.1. Some people say that you can use the cutoff value of 0.2, but you can see that all the values of for here the tolerance is greater than 0.1 or 0.2, so we are good to go. And for VIF, the cutoff value we used is 10. VIF should not be greater than 10%, or are way less than 10, 1.1.1.1. So which means that our independent variables are not, there's not an issue of multicollinearity, so we are good to go. Okay. Now here we would.
Dr. Karim?
Yes.
What if we have an issue with this? Like, for example, there is actually a difference, or it is more than 10, for example. We will have to do different tests?
Yeah, look, either you have outliers on that variable, or that variable is strongly correlated with one of the other variables. Then you have to remove that from your analysis. Either you try to fix it like by, if you have not worked on the outliers, go back, work on the outliers, work on the normality. If after working there, even if the values are higher, just remove it from your analysis, which means that that shouldn't stay in the regression equation.
Okay.
Okay, so now we look at the beta values. Now, if you look here, how many alcoholic drinks per day you have consumed? We typically look at standardized coefficients. So these are my standardized coefficient. These are the unstandardized coefficient. So we look at the standardized coefficient. The standardized beta value is 0.01. As you can say that it is, you can see it's too low. The strength is too low because the beta basically tells you the slope of the line, which is between the 2 variables. So the higher the beta is, the steeper the line would be, which means the more stronger the relationship is. So you can see, you can look at the significance value. It is 0.822. So which means that how many alcoholic drinks you consume per day, that is not a predictor of your physical fitness. This is what our data is telling us. Okay. Our sleep per weeknight. Now, if you look at the beta value, it is standardized beta value. It is 0.149, and it is again not significant because it is 0.10. And we are dealing like here we are taking 95% confidence interval, so it should be less than 0.05, which means that the number of sleep hours you sleep, that is that is not a predictor of your physical fitness. Age. If you look at the value of the standardized beta coefficient, it is minus 0.007. Now, this is again not significant. The only significant predictor we found here is energy level. Now, if you look at the energy level, the beta coefficient here is minus 0.37 and significance value is 0.00, which is less than 0.05. And this is negatively, predicting physical fitness, which means that if energy level is high, physical fitness is low. That's against the common sense, isn't it? But I know this is coming up from the data. So this is how you, so if you look at our hypothesis, only one hypothesis is spotted, but let me see what was the hypothesis we made. Energy level positively predict physical fitness. So this is also not spotted because, so none of our hypothesis is spotted because we predicted that energy level positively predicts, physical fitness, but in our data, it is negatively predicting physical fitness. So this I just prepared this model out of nowhere because there's no theory behind that and like that, but just for the demonstration purposes. So that's it. That is the end of our third day. So today I'm leaving you on time. Meanwhile, if you have any question, you can always ask me. So we have 4 or 5 minutes. You can talk to me. After that, I have two, private meetings with 2 from the groups for maybe 5-10 minutes. So, but these 5 minutes are just open to any question, any discussion.
Doctor, I think mashallah, the workshops are very, very comprehensive. They are much more than basic. Yeah, we learned so much from you. Yani. Thank you very much. And we are greedy. We really want you more of these workshops, Doctor. Yani, inshallah, in the future we will see more, inshallah, hopefully. So thank you so much for putting this effort and explaining every detail. Yani. Thank you very much.
Thank you very much. I really enjoy it, and I wish all of you best of luck. This was just a basic stuff, and I think this is much, much, much more than that. So if in future CGS allow me for another one, we can just build on this and take it from here and talk about a more advanced stuff like factor analysis, and then we have multi-level, we have this mediation, moderation, so many. It's an endless word. But at least you have the basics in place, and if you know the basics, from there you can just build on that. There is a lot of resources which are publicly available: YouTube, Google, websites. So you can just explore it further. And if you have any questions, you can always send me emails, and if I have time, I would be more than happy to help you.
Thank you so much, Doctor. Really appreciate your efforts. I wonder if you may recommend any book that is very simplified and right to the basics. I'd very much appreciate it.
There's one book which you can find on the slides, the first slides. There's a book written by Exploring SPSS, Exploring Statistics with SPSS by Andy Field. That is a wonderful book that doesn't talk about the maths and it's only on the, and I'm sure all of you are interested in the application. You're not interested in learning what is going on in the background. So that is a wonderful book for people who do not have a background in statistics and maths. It's only talk about the application part, that for what kind of problems, what kind of tests you should be using, and how to interpret the output. So I think that is the book. I have the PDF with me. If you want, I can just put it in the folder, share folder, and you can download it from there. Yeah, my email is, I'm just going to write it here, abeul.krim@edu.ac.ae. So this is my email. If you have any questions, any doubt later on, you're most welcome to send me an email. So inshallah, I'll try my best to get back to you.
Thank you so much, Doctor, for sparing your valuable time and for this informative and practice session. Thank you so much. And also for the attendees, I would like to remind you to fill the feedback form before you leave the session, because it will be very useful for us. Let me put it again. Yeah, I just put it in the chat box.
And today's presentation is in the share folder, the link which I shared with you on the first day, the Dropbox folder. So if you want me, I can share that again, the link for an easy access. Let me do it one more time. So you have both the presentations, you have the data file, and you know, the exercises which I gave you, you can do it by yourself, and I'm sure that some of you might have done it. So this is the link to that, to the Dropbox folder where you have everything. Okay, so two of you who wants to talk to me, so please do not end the session. So we can just talk about here, or you want to talk privately? Nigat and Ibtisam, right?
Doctor, shall I stop recording then? Now?
Yeah, please.